Hello, everyone. Welcome to this workshop on bringing natural language processing to the enterprise with Katie Gross. My name is Faraz. I'm one of the co-organizers at TMLS, so welcome. Just before we begin, if you have any questions, please feel free to ask them in the chat with the queue in front so that we can collect them and we can address them as we go along in the workshop, or we'll answer them towards the end. And just a quick reminder that all the talks for tomorrow are hosted on Hopin. You would have received an email earlier today or last night with the access. If you haven't received that, please do check your junk mail. If you still don't find it, please shoot me a message in the chat. I'll be able to help you. So it's my absolute pleasure to introduce Katie. Katie Gross is the lead data scientist at Dataiku, where she helps clients across industries develop AI solutions. Previously, she's worked as a data scientist at a marketing science firm, Schireson, and as a freelance data scientist at IBM and a dating app, Radiate. Katie holds a BA in economics from the Colgate University. So welcome, Katie, and over to you.
Awesome. Thanks so much. And thank you everyone for joining. So today we're going to talk about some key kind of fundamental concepts within NLP or natural language processing, and some key techniques. And yeah, as you just mentioned, please just throw any questions in the chat, and I'll either answer them live or at the end if we've got time. So agenda-wise, oh yeah, good point. Please throw a Q in the front so that we know it's a question. So we'll start with a little intro to NLP, then we'll talk about text cleaning methodologies, then we'll discuss vectorization, and I'll talk about what that even means, and then some key NLP techniques. So NLP intro. So first, to just kind of take a step back here, and we can think about kind of where NLP fits in within AI, machine learning, and deep learning. So if we take a step back, we can think about kind of this. I like this, this little image here, kind of, I think, outlines it well. There are others that have even different formats of circles and things like that. But AI is really just an umbrella term for any computer program that does something smart that we previously thought only humans could do. So something even as simple as like an online checkers game where it could be just simply rules-based is also a simple application of AI. When we do talk about AI, though, we are most often talking about machine learning, or at least when you hear AI used, that is most frequently what people are talking about. Machine learning refers to teaching a machine to learn from experience without like explicitly programming it to do so. There's two different types of machine learning. We're not going to get majorly into this today, although some of this does overlap with NLP concepts, so it's good to just review. Supervised learning is about making predictions about something in the future. So for example, looking at past transactions, credit card transactions, to predict whether or not a new transaction is fraudulent. Or Netflix predicting what movies you might want to watch. Those are simple examples of supervised learning. And then unsupervised learning is more about discovering underlying clusters and patterns within your data. So understanding certain groups, and often those two are actually used together. Deep learning is a subset of machine learning that is just kind of a category of algorithms that use neural networks, which are based off of the way that the human brain works and makes decisions. So this is used for often much more complex machine learning tasks. And this has really been kind of responsible for a lot of the boom of AI over the last few years. And then we've got NLP, which is what we're going to be talking about today. So a lot of NLP does overlap with machine learning, where we're learning from the past. Other times we're just doing some more simpler kind of rules-based decision making, and we'll discuss some of those different techniques later today. So where NLP is used, so I discussed kind of what it is now. Some of the ways in which it's used in your day-to-day life, email spam filtering. So when emails are kind of automatically sent to your spam or regular inbox, driving customer sentiment. So brands want to know what are people saying about us online, you know, on Twitter, on Instagram, and kind of maybe we, you know, put out a new product. We rolled out like a new version of our app. Do people like it? What are people saying? And kind of automatically parsing through that without needing to, of course, read through every comment. Fake news identification, obviously, you know, a hot topic right now. And so, you know, Facebook, Twitter using a lot of NLP to try to automatically detect that. Then automatic language translation. So, you know, sometimes you go to a website that's maybe in another language and it might suggest, would you like to translate to English? That's using much more advanced NLP techniques. Then we've got speech recognition like Siri and Alexa. So first, your speech, your vocal speech is converted to text, which is then converted to a series of numbers so that the machine can understand what you're saying. And then generate some speech and response, and then chatbots as well. You know, you go online to some site, maybe you're looking to, you know, order some clothing online, and they might say, hey, can we help you today? And of course, that is also using NLP. So I like to convince people that things that I'm working on are hard before I dive in, so they're impressed. But NLP is notoriously very, very hard because you think about like learning a new language is really hard. You know, there's like sarcasm, irony, jokes, and context, all these things that make it really hard as a human being to understand a new language. Now, when we talk about a computer understanding a language, it is incredibly challenging. So at sometimes even no amount of text cleaning can make something perfect, but just to kind of understand some of the challenges with NLP, first is syntax. So syntax is really kind of how words are put in some certain order that communicates a message. So the girl bit the dog is using the exact same words as the dog bit the girl, but obviously the order of the words conveys a very different message. So if we were not looking at the order of the words, then we wouldn't really know the difference between those two sentences. So some of these things also will later come into play when we kind of evaluate one technique versus another, where some look at order of words, others don't. And of course, you can see how there's a trade-off there. Then semantics is really the study of meanings, the meaning of a sentence. So here we have, when the hammer fell on the glass table, it shattered. As human beings, we probably know that this is referring to the glass table, not the hammer, but this "it" is actually used very ambiguously. And so if you didn't understand that it was a lot easier for glass to shatter than a hammer, you really wouldn't know necessarily what that "it" was referring to. So that is something else that's just hard for a computer in this context. And then pragmatics is the study of contextual information on a sentence. So here, like, what a flood. You might know based on the conversation and what had been discussed before, or like the sentence prior, whether that was referring to like a gallon of milk spilling or like a flood that devastated an entire city. Obviously, those are very different sentences, and the kind of the context here helps you to understand that, and all of this kind of comes into play more later on. And so There's been tons of advancements in NLP and kind of advanced deep learning techniques within NLP that have made like Alexa and Siri and Google search smarter and more efficient and even better able to understand things like this, but still very, very challenging. A bit of terminology before we dive in any further. Oh, I just saw the question. NLP solutions for small businesses. So this was a question in the chat. Let me go back a little bit. So yeah, I mean, I guess it depends on the industry you're in. So could you give me an industry example just to make this a bit more, I assume we're talking about like a retailer, but so manufacturing, okay. So I'll actually tell you a use case that I'm actually, a project I'm working on with a customer right now is actually a networking hardware and software provider. So they manufacture like equipment that builds computers. And so they are actually looking to make their support team more efficient. So people email being like, my Wi-Fi is not working, my router's broken, etc. And they've got all of these different repositories of online documentation. And what they want to do is look at the text from the support ticket from the customer who's saying, you know, I have this product and it's not working, blah, blah, blah. And they want to automatically try to match this support ticket with the proper documentation. So what we're actually doing is, I'll get into the techniques more later, but we're actually using NLP to convert this text into a vector, so a numerical format, and then actually compute similarity between the service request that's come in and the documentation online to find what the documentation that's most relevant to answering that support ticket. So that's one example. Obviously, you've mentioned chatbots. Another big thing is customer sentiment, as I mentioned. It of course depends on kind of your business goals, but that's a big one as well. Another thing is like, I mean, this is more retail, but like trend detection. There's really quite a lot, and it also the best way to think about this is also kind of like, what are my business goals? And then backing into, okay, well, how can I solve them? Rather than working backwards, like, okay, what are the things I can do? And then what might it solve? Well, you know, it's always most important to think about the goals of your business rather than like, what is the fanciest, sexiest new technique? Because, you know, at the end of the day, you want to make sure you're just solving the problems that are most important to you. But good question. Okay, so a bit of terminology before we move any further. So a corpus is a data set of text. So this might be newspaper articles, emails, tweets, Instagram comments, etc. Then a document is one single entry within that corpus. So if we've got a corpus of emails, a document would be one individual email. And so if we imagine this as like a standard, you know, tabular data set, we would have the corpus. Each like record in our data set would be one email or one document. Then vocabulary is a list of all the unique units, which are typically words, but can also be like bigrams, which is like two words together. So like thank and you together. We'll talk more about that later. So vocabulary is a unique list of all of the units in the corpus, and a token is one specific unit and actually a reference to one specific unit in the document. So it's referencing a specific word. And so these, we actually won't dive too much further into like this terminology, but it's just important to kind of understand these different things before we dive any deeper. So now let's talk a bit about text cleaning, which is typically kind of the first step of any NLP task. So we're going to talk about 4 key text cleaning tasks. So first, normalization. then stop word removal, stemming and lemmatization, and tokenization. And if any of these words mean nothing to you, just wait, you will soon understand. So first, and actually, I guess before I move further, yeah, text cleaning is super, super important to any NLP task because if we remember kind of what I was talking about with like syntax and all these different things, if we've also got like super messy text and we've got like words that are unhelpful and all of these things, it only makes deriving meaning from our text even harder. So first thing, and often first step, is normalization, which can include actually a lot of different kind of subtasks. One of these things is converting all text to the same case. So you wouldn't want the word run with a capital R to be different from run with a lowercase r. You want those to be considered the same thing. So often just converting all text to the same case, typically lowercase. Removing punctuation. So you don't, sometimes some punctuation can be helpful. So for example, like an exclamation point or a question mark might in some ways change the meaning of some text. So of course, like what punctuation you do and don't remove can get quite funky, but typically like things like periods, commas are very safe to remove. But then also it can be complicated with like dashes or kind of concatenated words. And there's, of course, a lot of decisions you might need to make there. And then like miscellaneous noise. So for example, like numbers, or you might have, for example, like user IDs that have like numbers in the middle. And maybe you want to automatically detect words that conform to a certain pattern and say, okay, I want to remove these, or I want to change these words in a certain way. Or often text data might come from information that's been scraped from the web. And if so, you might have weird like HTML tags or just kind of some funky formatting that you might want to clean up. Or like maybe it's come from Instagram and you have like the username at the beginning and you want to get rid of that. And so what's called regular expressions, or regex, can be used for pattern searching to say, okay, if it's like at and then some kind of sequence of letters and numbers, I want to ignore it, or I want to extract it and throw it in this separate kind of column of like usernames. So there's quite a lot that can happen here, but these are just all different ways of kind of initial normalization to convert your text to a consistent format. So here, if we had these two bits of text, and we'll use these as examples throughout. I went for a run yesterday, exclamation point, and I love running outside in the summer. Here with normalization, we would just be removing all the punctuation here perhaps, and maybe moving everything to lowercase. Then next thing is stop word removal. So stop words are common words in a language that hold very little information, and they can be customized. So here, for example, these are words often like and, the, that, but. So when you talk about, let's imagine we're trying to classify text to understand like what this what this sentence is talking about. A word like and the probably aren't really that helpful, and they might just kind of like clutter the work that we're trying to do and sort of hurt our classification accuracy if that were the text at hand. I mean, the task at hand. But generally, you're trying to like understand what this text is all about, and these words don't help. You can also often customize stop words. So for example, maybe you've got a lot of like cooking related text, and words like teaspoon and tablespoon might not be helpful, and they're very common, and you just kind of want to get rid of those. So this is another thing that will help clean up your text. And of course, is something that you can really customize a lot based on the subject matter at hand. Next thing is stemming and lemmatization. So these are ways of kind of getting to sort of a root word. So stemming is really just kind of more rudimentary, and you're just stripping all suffixes. So if you've got the word like assign, you're just, and maybe you have like assigns, you would just chop off the S at the end, and that would just be stripped down to assign, or assigning would just be stripped down to assign. The word assign would be the same whether you stem or lemmatize, which lemmatization is about obtaining the root form of a word. But let's imagine some words are a bit more complicated in the English language, where you don't have this clear kind of root word that has the exact same letters. So if we think about the word be, and we the conjugations there are kind of all over the place. So like being would be the same whether we stem or lemmatize, but if we had like past tense was, and we want to convert that to present tense, with stemming, there's not really a clear way to do that. That would just remain that word was. Whereas lemmatization would say, okay, we're going to convert was to present tense, and was equals be. So this is slower, but as you can probably see, definitely more advanced, and really helpful when you are trying to just kind of say, okay, what is this word talking about? And we don't want assign or assigning to be considered separate words. We just want them all to kind of convey one meaning here. And so that's kind of what this is all about. So hold on. It seems like the question is, it seems like lemmatization does a better job so you don't get weird cutoff words with stemming. For a large data set of text, would you consider just foregoing stemming altogether? So lemmatization is almost always like better from a text cleanup and like accuracy standpoint, but it's very slow. And if you have a huge data set or like memory constraints, stemming is easier and faster. So it's basically, if you have the means, you typically want to lemmatize because it is often just going to be more sufficient. But if you maybe like you can't, sometimes like maybe you don't have a strong enough machine, or your data set's just too large, and stemming is a lemmatization maybe is gonna you're gonna like run out of memory, or it's just gonna take too long and you don't want to wait. So that's really kind of the main trade-off. Can stemming be a subset of lemmatization? So I guess, I mean, sometimes stemming and lemmatization do the same thing. Other times they don't. It sort of depends on the word and the like morphological analysis of that word. So the word like assign would do the same thing, but the word be, this would like if you were to use stemming on these, being and been would be reduced to be often, but like was, were, these would all be separate words. There are also like different types of stemming and different types of lemmatization that will even like chop words in different ways. You don't need to worry so much about that for the purposes of this presentation, but it is worth noting. But basically, stemming is faster, but a bit more rudimentary. Lemmatization is definitely more advanced, but slower and more memory or computationally expensive. So example here with our text. So here, if we had went, so here we've already removed the stop word. So we just have like went, run yesterday. With stemming, went would not change, whereas with lemmatization, that would change went to go. So here you have that kind of present tense, and then going would also be kind of considered the same meaning as went, as far as like root form. Then here, then run and running. So goal here is all just about converting words to kind of a standard tense. Again, there could be situations where you want to preserve the tense. And again, you can see how this can get complicated, but most of the time, present tense is really like sufficient for your needs, and just a question of like, do you care about processing time and memory consumption, or do you just want something really fast? Then the last thing we'll talk about as far as text cleaning is tokenization. So as I mentioned earlier, it's one of the vocabulary words. Tokens are just kind of smaller units of text. So here we're really just kind of taking our text and we're saying we're just going to convert it to like a list of strings. So here we'd have like run and yesterday, just considered like two different like units. And that will make a lot of sense kind of why this even matters once we talk about vectorization, which will be the next topic. But there are some different methods of tokenization. The key kind of difference is whether you want to consider unigrams, bigrams, or trigrams, or some combination of those. So for example, as I mentioned earlier, like thank you, those two words together hold a very different meaning than they do separately. There are many other words like this. So sometimes you don't want to just consider each word individually. You might want to also consider groups of words together. And tokenization will allow you to kind of define how you want to do that. So once we've cleaned our text, we got kind of nice text that looks good. We'll now want to vectorize it, which means we're converting our words to some sort of numeric format. The reason for this is because machines don't know what words are. Your computer does not know what a word is. When you write any code, anything, this is always, ultimately, anything is converted to some set of zeros and ones for your computer. But as far as like machine learning goes, we need to convert this to a numerical format so that we can maybe compute similarities, or we can add and subtract, or we can actually feed this text as inputs to a machine learning model. You can do things in different orders. Tokenization is actually often done first. I kind of showed it last here just because it's easier to understand, like tokenization and then vectorization. You can play around with the orders. So for example, like I'm trying to think, thank you. Yeah, so if like you wanted to preserve like a word as part of a token and not have it removed as a stop word, you could of course tokenize first. So you can see how this can get quite complicated. But yeah, okay, so just for sake of time, I will continue on here. So yeah, different ways of vectorization, and the whole point here is to convert our text to some sort of numbers so that the computer can understand it and do something with it. So first we'll talk about actually traditional methods. The two kind of key traditional methods are bag of words and TF-IDF, which we'll explain in a second. Then we'll talk about word embeddings as kind of a general concept, and I'll just dive into one of the like most popular word embedding algorithms, and then briefly mention some of the others. And word embeddings are much more advanced and have really been kind of responsible for a lot of the major kind of developments in NLP over the last few years, and it's a very hot topic. So traditional bag of words, or called count vectorization, is very simple and rudimentary. We're literally just counting the number of appearances of each word in a document. So if you're familiar with one-hot encoding for categorical information, it is the same idea. If you're not familiar with that, ignore what I just said. But the idea is here, we're going to take our text and we're going to convert each word to a column in our data set. And then we're just going to give it either a 0 or a 1, which will correspond to whether or not that word appears in that text. So here at index 0, like the first document here, we've got just run and yesterday. So those are each a 1 and everything else is a 0 and so on. So here we can see run is a 1 for both of them because it appears in both texts. And so if you were, let's say, doing some text classification, this would be, these zeros and ones would just be fed in as features into your model. Talk more about that in a moment, but the next kind of slightly more advanced method of like traditional vectorization is TF-IDF, where here we're still just generating one number for each word, but now we're getting kind of this measure of originality, and kind of it helps us understand how meaningful a word is in classifying a document. So what we do here is we multiply the term frequency, which is where TF-IDF comes from by the inverse document frequency, which is the frequency of that word in all documents in the corpus or in all of the text. So really what that's saying is like, if a word appears in like every single document, it's probably not that helpful in like classifying that document. So for example, if every single bit of text like uses the word run, then run is probably not that helpful in like saying, okay, this is talking about this specific type of running, or this is talking about running in the summer versus running in the winter. So that's kind of the idea here. It's really just getting at the originality of the term. So here, since like the word yesterday only appears in this text, and this text is only 2 words, it might be weighted more heavily and more helpful in kind of like classifying what that document's talking about. So here's just kind of an example of kind of how this might be computed. I think we can kind of skip through this, but the idea is you just have the term frequency for each document, the inverse document frequency across all the documents, and you kind of just multiply these 2 terms together. You don't have to worry so much about the math, but it's just about capturing originality of a term and helping to kind of better understand what that document's talking about. Whereas like count vectorization is just telling you how common it is, right? So this doesn't tell you anything about whether, how kind of original a word is. So this gets you one more step along the lines of like classifying a given document. But the drawback here is that we're not looking at context at all. So if we think about like the sentence, have a good day and have a great day, good and great are just different words here. They're not, they're just as different as day and have. We don't understand here like that these words are actually being used in a very similar way and convey like a similar meaning. We're just understanding that, okay, they're different words and maybe used with a certain level of frequency. So what word embeddings are all about is actually using neural networks to generate entire vectors for words. So here, for example, the word run with TF-IDF, you might have this one set kind of number. With a word embedding, you're actually going to generate a whole vector, which is going to be a whole list of numbers. So you might have like 100 numbers that help to capture the meaning of that word. So you just have a lot more information about each word. And so that helps you to really understand kind of the context with which a word is used, and also actually compute similarity between words. So you do need a lot of data to often, if you were to kind of train your own word embedding model, but often you can just kind of use some out of the box solutions here. So to understand this, or actually a bit better, and actually we'll talk about word2vec in more detail in a second, but I mentioned that you can compute similarity between words, and just to kind of get a better understanding of what that means and kind of what these angles are all about. The way that we can measure similarity is using, or one way is cosine similarity, which allows us to look at the size of the angle between two words. So because we've generated a vector, if we imagine this in 2 dimensions, here this might be like 0, 4, and this might be 0, 3. We can actually compute the similarity between these 2 words by looking at the size of the angle. So if the angle is really small, then we can kind of infer that these 2 words are probably pretty similar. And what cosine similarity is doing is just converting this angle to a measure between 0 and 1, -1 and 1. So 0 means not similar, and -1 means similar, but like opposite in some way. Sorry, I'm just reading this question. Bag of words was nothing notorious for. So bag of words is definitely looking at context. TF-IDF. So yeah, TF-IDF you can use like unigrams, things like that. Bag of words. I'm trying to think. Oh, sorry. Wait. I thought you were saying word back. So you can. I'm not sure if I totally understand this question, but you can use. I believe you can still use bigrams and things like that for bag of words, but the problem with bag of words is that you're not getting any information about the frequency or like the originality of a word. But neither of these are looking at like the actual context. They're just, TF-IDF is just going to tell you like how common a word is across that document, but you're not going to understand, okay, this word is often used alongside these other words quite in the same way that that you can with word embeddings. So Word2Vec, which is just kind of one of the oldest, or it was kind of the first word embedding methodology created, and a helpful one to start to understand this, and the one that we'll kind of dive into, was developed by Google in 2013 and uses 2-layer neural networks to generate some vectors for individual words. And the way you can use this is either by using pre-trained models. So Google actually trained Word2Vec models on Google News. So on like all of the text in like every Google News article at that point in time. And so you can just use like the Python package of Word2Vec to go ahead and start like doing some text classification and things like that. Or you can, if you want to, maybe you've got some text that's like very specific to your company or your industry, and you've got like some words that wouldn't ever have been included in Google News, so maybe like product names and things like that. You can train your own Word2Vec model, or you can use transfer learning, which is kind of a method of saying, okay, I'm going to build off of this neural network that exists and just kind of try to learn some additional words of like from my my corpus, like on top of that. But basically, the way that it's the reason this is valuable is, so now kind of what I was showing before with this cosine similarity stuff, what we can do here is, is actually like get this measure of similarity between words. So this isn't possible with TF-IDF or bag of words, because with those you just have one number. It's one dimensional, and you can't really get this kind of complex measure of similarity between words. Here you can actually perform like mathematical operations to say king minus man plus woman equals queen. Here, so this is a gross oversimplification, because your neural network is not necessarily going to have like these very simple like is male, is royal, whatever, but you can imagine that kind of maybe you've got a vector that's generated that's like got, it's maybe of length like 50. And so there's 50 individual numbers, and each number might be kind of capturing some sort of question like this. It's often not so neatly defined like this, and you can't actually parse out what it is. That's the beauty of neural networks. They're very smart and advanced, but you also don't always know exactly what they're doing for you. But the idea is that you might be actually each number might be answering some sort of like question about that word, and so then you can nicely kind of compare words in vector space. So what else did I want to say? So here, yeah, we can make really accurate guesses about a word's meaning based on past appearances. So maybe we can say kind of like this word is often used next to this other word, and so on. And so the output of this is this vocabulary where each word has a certain vector attached to it. So again, you can use just kind of that pre-trained out of the box, or you can train your own word2vec models. And so there's kind of two different ways of that word2vec can generate these vectors. I don't want to get into too much detail here, but basically with a common bag of words, it uses the surrounding words to predict the target words and then update some weight. If you don't know too much about neural networks, this is kind of a whole other bag of like a whole other can of worms, but essentially you're saying, okay, I'm going to use like have or a and day to predict what the word is in the middle. Maybe I'm trying to predict the word good. I'm going to say, okay, how well did I predict that word? How far off was I? Update some weights, and then ultimately generate some final word vectors once I've kind of fed like all of my text through this model, and then learned some vectors for each individual word. Skipgram does it the other way around. I wouldn't worry too much about these methods because this is kind of quite advanced here, but just know there's different ways of actually generating these vectors. And the whole idea here is that you are looking at the surrounding words, whereas TF-IDF is not, oh, you're right. I think I might have miswritten that. Thank you. I knew that sounded wrong. And so anyway, you're looking at surrounding words and not just looking at each word individually. I'm trying to keep an eye on time here, and so I'm gonna kind of skip this, but just note that there's tons of other word embedding algorithms. I'm gonna hold these questions for the end, just because I'm realizing I'm moving a little slow. A lot of them are kind of using are using different parts of words or moving bidirectionally, and so just different ways of actually looking at context to understand kind of what this word is about, and kind of comparing words and things like that. So many different NLP techniques that we can use to actually do something with this text. So we've cleaned our text, we've vectorized it, so we've converted it to either a number or a list of numbers, and now we want to do something with it. So I'm just going to talk about 3 common NLP techniques. There are many, many more, but these are some kind of common ways of actually deriving some further meaning from our text. So text classification is quite simple. The idea here is, so we vectorized our text, and now we're just going to use that vectorized text as inputs to our model. So here, for example, we want to predict whether or not an email is spam or should go to our inbox, and different kind of algorithms that you can use, either just any kind of regular classification algorithm, often like naive Bayes, support vector machines are frequently used for text classification. And the the same way you might have other regular numerical inputs, and just kind of train your model in a regular way otherwise, just that now each word is, or each token at least, is a new column in your data set. Next is topic modeling. So topic modeling is a method of clustering documents to automatically identify topics and some keywords associated. So there are a few key methods of topic modeling. LDA, which uses probabilistic modeling. We'll dive into a bit more detail on LDA in just a second. Then NMF, which stands for non-negative matrix factorization, and uses more kind of linear algebra to generate different topics, or different deep learning methods as well. For kind of sake of the presentation, we'll just talk about LDA. And kind of how it works. So LDA stands for latent Dirichlet allocation. So latent means hidden. Dirichlet is a probability distribution, and kind of allocating different terms to topics. So the goal here is to learn the topic mix within each document and the word mix within each topic. So here, with this example, we have different questions which have contain a mix of topics, and we want to say, okay, what topics exist in each document, and then also understand what each topic is kind of all about, and what are the keywords within each topic. And this will help you actually kind of group your text into some meaningful topics. So, for example, maybe this first one is 100% topic A. The second question, what is the most hated NFL football team of all time, is 90% topic A, 10% topic C. We say, okay, but what do these topics actually mean? Then we actually look at, okay, topic A might be consist of these certain words. And so then we understand, okay, this is like talking 100% about sports. Maybe this one, so topic B is about sports and politics, and this is kind of capturing those two. So how this actually works, or actually before we dive into how it works, one nice benefit of LDA is you have this really nice Python package called LDA Viz, or PyLDA Viz, which allows you to actually visualize the words associated with each topic. So you can hover over a topic and kind of say, oh, okay, topic number 4 consists of these words, and then go ahead and like manually label your topics. And maybe topic 4 is about politics, and topic 1 is about sports, or whatever. And you can also kind of see how close different topics are, and then maybe actually decide that you actually want to look at fewer topics because there's so many that are so tightly overlapping. So how it actually works is you actually, as kind of only have to set one input, which is really just the number of topics that you want to learn, and that's kind of the one hyperparameter that you can tune and set. And then what's going to happen is the algorithm is just going to randomly assign each word in each document to one of the topics. And so it's going to say, okay, this word number 1 is assigned to topic A, word number 2 is assigned to topic B, or whatever, and kind of just do that very randomly. And then, so it's going to do that for every word in every document. And then it's going to go back through and reassign each word to a given document based on 2 things. One, how often the topic appears in that document. So let's say you've got politics and sports, how often that like sports maybe appears within that document, and how often this given word appears in a topic overall. So if you've maybe assigned the word like news to sports, you might understand that actually you should reassign news to politics based on kind of some probability threshold, and kind of continue iterating through, and then you'll kind of generate some final both here mixes of topics in documents and word mixes within topics. And so, of course, here you might have overlap where some words might appear in multiple topics, and that is kind of a nice thing here. Whereas like a much more traditional clustering technique would require that one word was only in one topic. So that's generally how LDA works. And then the last thing that we'll talk about is sentiment analysis. So sentiment analysis is all about automatically determining sentiment from some input text. So here, actually, sorry, one last thing that I didn't mention here is, again, like when these topics are just going to be like topic 1, topic 2, you're not going to know the meaning of the topic. It's then up to you at the end to look at the word mix within each topic, and here then say, oh, it looks like this is kind of about like sports. Not every topic is always so clear, but looking at the word mix will give you kind of a general topic, allow you to kind of generate some like human topic label. So sentiment analysis here, we want to maybe determine sentiment from input text and understand maybe, as I mentioned before, like you released a new product for, your company released a new product, and you want to understand, do people like it? Are people saying good things or bad things about it? Just kind of at a simple level. So here's some key methods of sentiment analysis are: one, using a very rudimentary out-of-the-box package called text blob, which is actually very frequently used, and we'll talk about this in just a second. It's very simple and not using machine learning. It's just kind of in that like larger bucket of like AI. You can also use standard classification algorithms or deep learning. But we'll talk about how text blob works, because it's actually quite frequently used and surprisingly like accurate. But basically what you do here is order does matter here, because you want to understand if someone says, I am not happy, you want those two words to kind of remain in that order. And you also want to be careful here about stop words, because words like not or but might really influence the meaning here. And so essentially the way that this was created is a bunch of linguists actually went through the entire English language to generate WordNet, which is just kind of a like dictionary of sentiment scores for all words. So at like almost every word in the English dictionary has some sentiment score. And what it does is it just averages the scores across a document. And if you have like the word not before another word, it just negates it. So if you have not happy, and happy maybe has a sentiment score of 0.8, it'll then be negative 0.8. So it's pretty simple, but it actually works quite well. And any word with multiple meanings will have those two sentiment scores averaged. And so then you kind of come up with, okay, what's the overall sentiment of this document? So that's those are kind of the key items. So some key takeaways, and then I'll see if I have a minute for one of these questions. So NLP requires diligent text cleaning. Vectorization allows us to use text as numeric features in a model. There are tons of different applications, including sentiment analysis, topic modeling, and text classification. And advancements in deep learning are really paving the way for the future here. So yeah, to get to the question about topic modeling. So here, maybe you've got some raw text data and you just want to understand what are the different topics, or you want to kind of like classify text, but you don't even understand, you don't even know what the topics are that you want to group your text into. And you're kind of saying, okay, I want to group together kind of all of my these emails that are talking about sports or technology. It's often kind of just about like grouping text. Can also be used as like an input to like a supervised learning model. So maybe you want to first group your topics and then say, okay, this is associated with technology, and use that as an input to like predict the something else about this text. So we only have like 1 more minute, so I'm not going to get into transformer models like really right now, but essentially the way that they work, and here is they look both like bidirectionally. So the question was around, some key transformer models are BERT and GPT. So rather than looking at left to right, they look left to right and right to left. So it allows us to just kind of, one, be actually a lot faster because you can parallelize the training, and just more accurate because you're just really getting a lot more information about the way in which a word is used. And so as you can see, I mean, these algorithms, like I created this presentation a little over a year ago, and there have even been like more updates since then. So you can see, obviously 2019 is very recent for new algorithms that we're using. So lots of exciting stuff happening there. And yeah, that is all. So I think this probably wraps up this presentation, but are there any kind of final questions here? Awesome. All right.
All right.
My share.
Thank you so much, Katie, for a very fascinating presentation. Thank you once again. Thanks everyone for joining. The workshop is recorded, so we will be able to share that after the summit. We just got a question if you have a sec.
So yeah, topic modeling is similar to k-means clustering in that you're like grouping things together. The difference though, or one of the differences is that if you were to use k-means clustering, each word would only be in one cluster, whereas topic modeling allows words to appear in multiple topics or multiple clusters, which is often more realistic because like often one word can kind of be associated with multiple topics.
Awesome. So that kind of wraps up all of the questions for the workshop. Thank you so much, Katie.
Great. Thanks so much, everyone. Have a good one. Bye.
Thanks, everyone. Bye-bye.